Hello, everyone. This is the first part of the lecture of section 8.4. So this is the material you're supposed to study from today, Monday, March 29th. Okay? And don't forget that you have a Zoom office hour meeting today on Monday, March 29th from 9 to 10 a.m. Maybe this video could be uploaded after that time, but you will have from now on Mondays and Thursday Zoom office hours will be 9 to 10 a.m. So I chose that time same as your class time, so everyone was available at the time when you signed up for this class. So I believe that everyone can come to Zoom meeting office hour if you want. Okay, so, and then the rest of the section 8.4 is supposed to be studied this Thursday and on. All right, so that will be uploaded tomorrow or the day after tomorrow, by the morning of Thursday. Okay. All right. So here, 8.4 is about the other convergence test. So last time we studied section 8.4 that was covering integral tests, comparison test. All right, and then limit comparison test. Right, those three important tests today. But all those tests required is all about positive series, when your series have positive terms, at least ultimately positive, right? Now, today, for the first time, we will learn a test about something else. This is the alternating series. So, for example, this is best explained when we learned that this harmonic series divergence, right? This is a P-series test. P equals 1, divergence. What about alternating series? So, it is 1 minus 1/2. Keep going, right? Minus 1/6. Is it going to be divergent too? Okay. All right. Then, whatever that thing is, if it were convergent, that should be the limit of Sn, right? Partial sums by definition. Now, this is K runs from 1 to n. Okay. So, in order to understand this, let's draw the graph n versus Sn. Okay? And this is 1, 2, 3, 4, 5, 6. 6, 7. All right, this is 1. Now S1 is 1, right? This is 1. Now S2 is this 1 minus 1/2. So it's 1/2, right? Now you have to recognize that this one also obtains from 1, you drop by 1/2, right? Drop by right? And then, what is S of 3? From 1/2, you rise by 1/3. Rise by 1/3. So, drop by 1/2, and you recover by 1/3. Right? So that result is not gonna be totally back to 1, but recover some. All right? And then, from there, S4 is from that value, you're dropping by 1/4. From here, you're dropping by 1/4. So 1/4 is smaller than 1/3. Right? And then this is S1, S3. This is S2, S4. Now S5 is from there, you're adding 1/5. From there, adding 1/5. So minus 1/4, adding 1/5. Adding 1/5, right? Save it. Up by 1. So this is S5. And then, what is S6? This is S5. S6 will be from there, dropping by 1/6. S6. From there, S7, adding 1/7, right? So, now you see the pattern? Always, your current drop, size of drop is not as large as the previous rise. Likewise, your current rise is not as large as your previous drop. This is not as large as previous rise. This is not large as previous drop. So, that's why when you go from S1 to S3, drop, recover, but not as much. So S3 must be smaller than S1, right? Likewise, S5. So you have this. If you compare every odd term, this is decreasing, right? Forever. However, every odd terms, look at this, every odd terms is larger than S2 because, look at this. This one is, so S1 was larger, S3 is larger, right? So, because every odd term, okay, I'm gonna just finish this. Likewise, S2 is increasing. Right? Every even terms are increasing because rise and drop, but not as much. So S4 must be higher than this. S6 must be higher than this. right? Now, look at every odd term is larger than the next even term, right? The next even term is always greater than S2. So no matter what odd term you choose, this one is always greater than S2. So your odd term is a decreasing sequence, yet bounded below. That means this is convergent. Exists. Let's say SO odd term exists. Decreasing, monotonic, bounded monotonic sequence here. Likewise, your even terms is rising, increasing sequence. But every term is smaller than the previous odd terms, right? That previous odd term is always smaller than S1. So it is always less than S1. This is increasing sequence. This is increasing sequence, yet bounded above. So bounded monotonic sequence theorem. It has to have a limit, right? Now, these two numbers must be same because if you subtract what is it? There must be S0 minus S1. But this is fine. Summation up to 2n terms, 2n plus 1 terms, minus up to 2n terms. A1 plus A2 plus all the way to A2n plus 1, minus all the way to 2n, S2n plus 1. If you subtract, everything cancels, only this one is remaining, right? What is 2n plus 1? 1 over 2n plus 1 minus 1 to the nth power. 2n plus 2 power, right? The size is 1 over 2n plus 1. We know that this one is going to 0. That's why even terms and odd terms approaches the same value. Therefore, this one, odd term and term together will approach something. Okay? So, this alternating series converges. Even though this absolute value series was divergent, the alternating series is convergent. The key idea here was not only it is alternating, what was the key? Always the next drop is smaller than previous rise, or next rise is smaller than the previous. That means the absolute value, the size of the term is smaller. All right? So important reason is the absolute value series here is 1 over n is decreasing. This was the key to have this, right? Size of the absolute value sequence is decreasing. That will give you this. But in order to have odd term sequence and even term sequence convergent, this must be saying 0. That means, as Engelstein claimed, each term, the sequence, underlying sequence, must go into 0. Limit of absolute value of A, which is limit of 1 over n going to 0. These two were the key in the convergence of this. All right? Actually, any alternating series which satisfies these two conditions will have exactly the same properties like this. Okay? So we'll be converging. So we have the following theorem. Theorem 1. Alternating series test. Okay, so that is. By the way, I'm not going to write the definition. You see the definition? A series sigma AN is called alternating series if its terms are alternately positive and negative. So there are two possibilities. The first one, what is it? -1 to the n plus n minus 1 Bn. Bn is the absolute value of A. It is starting from positive, right? So the first one in the definition, this one is positive B1 minus B2 positive, starting with positive, like this one. This one, starting with negative. All right. So both of them are called alternating series. Okay. So Bn is the absolute value. This together is called An. So the theorem is that if this one is an alternating series and one of those two forms, all right? And these two conditions are satisfied. So basically, decreasing. This absolute value sequence is decreasing ultimately. Second, limit of this absolute value sequence going to 0, these conditions, then the series converges. Okay? This is exactly the idea. Okay? So this is the major theorem about something other than positive series, right? Certainly it's not always positive. Okay. Now let's do some examples. Example 1. Example 1. So the first one, what do you have? By the way, you have a lecture note, PDF file of lecture notes of this section and every section starting from I think 8.3 or 8.2. So you have to print them out and put it on the table when you listen to this video lecture. All right, and then you can write down some of the comments on the lecture notes. Okay. Here, this is n equals to infinity. Okay. We just proved, right? Absolute value series in this case. The absolute value series is 1 over n. It's definitely decreasing. And this one is going to 0. These two, therefore convergent. All right? We just did that. B. What about this one? Certainly this one is alternating. Now, just because it's alternating doesn't necessarily mean they're convergent. If you want to use alternating series test, you have to check these two conditions, right? Now this one, what is this one? 2n over 5n plus 1 does not go to 0. This one going to 2 over 5, right? The limit of this one. See? n. So this is negligible. So it approaches 2 over 5. So that means as n goes to infinity, the size will be almost 2 over 5. So it will behave something like minus 1 to the n, 2 over 5. It is very similar as n goes to infinity. It's just like positive 1, 2 over 5. Negative 2, almost positive 2 over 5. Almost negative 2 over 5. Almost 5, 2 over 5. Almost negative. This is almost oscillating, right? That means the original sequence is an diverges. It does not converge. All right? Therefore, that means sigma, the series is divergent. This is divergence theorem. You remember? Divergence theorem says that if series converges, then your sequence has to go to 0. So the contrapositive means anything not that limit an equals 0. Anything other than limit being 0 means limit is non-zero value or not even conversion. Anything other than limit of an equals 0 means this one is not conversion, so divergent. So this one, not even convergent, right? Limit does not exist, limit of n. Therefore, the series is divergent. Okay? Now, C, what is C? C is okay, this one. So Bn. So absolute value of An is n squared over, this is almost 1 over n, isn't it? N squared over n to the third. So we know that this one approaches 0. So satisfying this one. And, because this is almost n squared over n to the third, which is 1 over n, for all sufficiently large n, definitely we know that this one is decreasing, at least ultimately. All right? First and second. This is a pretty easy argument, right? Once n gets really large, this will behave almost like 1 over n, so therefore it must be decreasing. But in the lecture note I gave you a rigorous argument. That is, some people might think this is not rigorous enough. All right, I will accept this much as a rigorous enough argument, but if you really want to be really rigorous, then you have to use this. What is it? This is a mother function, right? Of absolute value sequence. See? Is f of n, right? Now, in order to show that this is decreasing, then you have to show that derivative is less than or equal to 0. That means if the derivative is less than or equal to 0, then it's decreasing. We have done this one, same thing in integral test, right? So in the end, I'm not going to follow this detailed calculus. It's really pretty simple application of quotient. In the end, you got that this one is x times 2 minus x to the third over x cubed plus 1 to the square. So this one, your derivative is less than 0 if and only if 2 minus x to the third less than 0, right? Now, we are considering only x is greater than or equal to 0. Note that x is definitely, we are talking about an, absolute value n of n, so n is greater than or equal to plus x. Among x greater than or equal to 1, this got to be negative, which means x cubed is greater than 2. So as long as x is greater than cube root of 2, which is about 1 point something, this decreasing. Therefore, graph of x is decreasing for all x greater than cube root, but at least greater than 2. That's why absolute value of an, which is f of n, decreasing starting at least starting from 2, ultimate decrease. Because of that, this alternating series satisfies these two conditions. So that's why it is convergent. Okay? Lastly, see, once you have an alternating series, you have to think about these two. All right? Last one was sine of n pi over 2 over n. Okay. Try to write it out. N equals 1. What is it? Sine pi over 2 is 1. So 1 over 1. Next up. N equals 2. 2 to cancel. Sine pi. 0. Right? And n equals 3. Sine 3 pi over 2. That's negative 1. So minus 1. Plus sine 4 pi over 2. Sine 2 pi. Back to 0. 0 over 4. 5. 5 pi over 2, which is 2 pi plus pi over 2. So it's coterminal angle to pi over 2. Sine pi over 2 is 1. N equals 6. 3 pi. Sine 3 pi is 0. And then n equals 7. 7 pi over 2 is coterminal to 3 pi over 2. Again, minus. You see a pattern? Every odd terms are, even terms are 0. Odd terms are alternating. So, strictly speaking, this is not alternating series. The way we define alternating series is, if you start with positive, the second term must be negative, and then positive, negative, positive, negative. This is not the case, right? So strictly speaking, it's not alternating series as we define it. However, if you drop to these 0 terms, and if you rewrite it, it becomes alternating series, right? If you ignore these 0 terms, it becomes alternating series. So we could have written this way. What is it? 2n minus 1. Starting from 1, right? And then n plus 1, right? This is alternating series. and your absolute value sequence is definitely this is decreasing, and the limit is 0, right? Decreasing and limit is 0. Satisfy these two conditions. Therefore, it must be convergent. Okay? It was essentially alternating series, convergent ones. Okay? All right. I wish I didn't erase that one. Now, alternating series estimation theorem. So, this is about the convergent alternating series through these two conditions. Okay? Alternating series estimation theorem. If you satisfy these two conditions, yes, we know that this is convergent. But then the Rm, which is defined as true value, okay? So then we know that, and let S be that value. Okay? This is your AN, and BN is the absolute values. Okay? If S is we know that these two conditions make our alternating series convergent, then, so I'm going to just write it. If you satisfy these two conditions as an alternate series, not only is convergent, when we write S be the sum of that series, then the remainder just like before, right? This is error when you use Sn as the approximate value. So S is the whole terms. Subtract Sn, that means remaining terms, right? Satisfies what? This one satisfies the size of the next, always, okay? That is very important here. And if you think about the previous thing, when you have a 1, 2, 3, so starting from 1, 1/2 down. See, this is up and down, but all odd terms are going down, all even terms going down, right? So that means they are approaching some value. S will be something like this, right? Going through this. This is S. It is up and down. So, if you use this one as 1, 3, 5, 7 as an approximate value, this is the remainder, right? This is R7, remainder. Difference between true value and this one, absolute value, is this size. That is less than this. What is it? The size of the next term. Always cross that. That means this size will be larger than this. The size of the next term. The size of the next term. Okay? Or if you use S6 as your approximation, then this is your R6. All right? Your R6 is definitely smaller than A7, absolute value of A7, right? So, if your alternating is satisfied by these two, then in general, this one says out terms going down, if terms going up, or the other way around. And then each one separately approaches this eventual sum, right? Always cross this up and down if you go through S1, S2, S3, S4. So the error by using current Sn is always smaller than the next term, because next term will cross S, right? So if you think about this, this is pretty clear. Okay? So we're going to use this theorem to estimate error of some of the terms. All right. Okay. Let's do example 2 here. Example 2. Find the sum of the series of this minus 1 to the n over n factorial up to 3 decimal places. Okay? So this is n equals 0 will be 0 factor is 1. 1 over 1 minus 1 over 1, right? 1. And then plus n equals 2 plus 1 over 2 factorial, 3 factorial, 4 factorial, minus, right? Keeps going. All right? And this one, this is 1 minus 1 plus 1 over 2 minus 1 over 6 plus 1 over 24 minus 1 over 120 plus 1 over 720 minus 1 over 5040 plus and so forth. Okay? Now, we want to approximate this value by choosing certain Sn. Some running to somewhere. We have to cut somewhere. So if you stop in 1, 0, 1, 2, 3, 4, 5. If you stop here, if you try to use this value as an approximate value, then the error will be smaller than this. All right? So we're going to I just wrote it this one as 1, 2, 3, 4, 5, 6. All right? No. 0, 1, 2, 4. This is S5. And this is S6. Starting from 0, right? Now S5, S minus S5 less than or equal to 1 over 720, which is, anyway, the maximum possible error is 1 over, this is 0.001 something. It's greater than, right? But we want to have an approximate value which is correct up to the third digit. But then when your error is larger than 0.001, our last digit, third digit cannot, we have no guarantee that our last digit of the approximate value is correct, right? So this is not good enough. But if you use S6, according to this, smaller than S7. If you stop here, smaller than this one, which is about 0.0002. Okay? It's less than, actually, slightly less than this one. Okay? So this is less than just exactly 5,000. So your error is less than 0.0002. And your S6 is what? 0.36856. So if you stop here, this is, the next term is negative. So our true value will be slightly smaller than this, right? But the error is, so you could subtract this much, right? And most this much. Even if you subtract, you get a something, right? So if you round here, still, you're going to get this, right? No matter how large the error is, it will be smaller than 0.0002. Either adding or subtract, but it has to subtract, right? You have to subtract something less than 0.0002. So it wouldn't change the value after rounding, right? So even though we don't know the exact value, true value, but we are certain that no matter what the true values of sum is rounded value to 3/3 decimal will be exactly 368.368. All right? All right. And later you'll show that this is exactly e to the negative 1. Okay? In 8.7. So we'll learn it later. So the remark, you can read it again. The remark says that if you stop somewhere using Sn as a value, okay, approximate value, then the error due to that approximation is smaller than the first term, which was dropped. Okay, the next term, smaller than that. All right, and then there are definition. I'm gonna if we have time. Okay. So first of all, I'm gonna introduce the definition of words. So first, if absolute value series converges, this is called absolutely convergent. Absolutely convergent. If and only if absolute value series converges. Okay? Then we call it absolutely convergent. Second, their series is called conditionally convergent. Conditionally convergent. If and only if this one is converges, but absolute value series diverges. Then we call it conditionally convergent. So example 3, determine if the following series are absolutely convergent or not. A, what is it? This one. What is the absolute value series? That is 1 over n squared. Conversion or not? Conversion. Because P series is greater than 1. P equals 2, which is greater than 1. Conversion. Therefore, it is absolutely convergent. Because absolute value series convergent. B. What about this? This is alternating harmonic series. Alternating harmonic. We just proved that this is convergent, right? Using this theorem, alternating series theorem 1, not that one. Satisfying these two conditions make it convergent series. What about absolute value series? That's harmonic series. P equals 1 diverges. So Original series converges, but absolute value series does not converge. Therefore, this is called conditionally convergent. So conditionally convergent series is convergent series. The series is convergent. It's just that its absolute value series does not converge. Okay? Now, I'm going to stop here. We're going to talk about this one a little bit more and then finish section 8.4. This will be uploaded. The second part of section 8.4 will be uploaded by Thursday, this Thursday, which is, what is it? April 2nd, I guess. All right. So, well, we'll continue from there. So see you next time.